So, good afternoon, everyone. Hope you are all doing good. So, today's lecture, so we are here in so today is September 18th. So, here we are here on September 18th, lecture 9. And so, what we will be doing is by today we will release one first assignment. The write-up will be posted, and what you have to do, everything will be there in that write-up. And you will get the deadline will be October 2nd, approximately 2 weeks. Deadline will be.
Abhi 1:30.
So if you would like to say something, please unmute yourselves. So great. Yeah. So the deadline is it will be October 2nd. There is one more thing also. We will be having October 9th issued in the next 2 weeks to form a project group of 2 students. Not for group of 3 students. It's not good. So let's just have group of 2 students, and so there will be approximately some 21 groups, 22 groups in the class. So each group will have a mentor. So Lavanya ma'am, Padmini ma'am, and me, all 3 of us will be mentors. So each of us will be mentoring 7 groups. The project ideas and the write-up, what should be the first write-up, what are the milestones, what are the expectations. That document will also be posted by latest by Monday. The group and your mentor will also be posted latest by Monday. So remember these 2 things. One, a homework will be released today. It will be due in 2 weeks. And then the project, the first phase of the project, that is defining the problem and the scope, that is due 3 weeks from now. And each batch, each group will have a mentor. So this is the plan. Any questions here? So while we suggest some project ideas, anything that you can bring from your own research background, or your experience. Let's say if you're working in robotics lab, or if you're working in NLP, LTRC center, or bioinformatics, or whatever if you have some specific research background, you can try to pick problems from that space, since you will have ample domain knowledge if you pick a problem from that space. What problems are important in that domain, and you can scope it out properly, and the resources that are available there, everything you will be knowing. But if you don't have anything specific like that, it is all right. We have some project idea.
Sir, if the group is already formed, then uh, should we send an email or any form is there to fill? How do we inform?
What is that? The group is?
No, if the group is already formed, then
Okay.
do we need to fill any form to?
Yeah, I will let you know. That's a good question. I will have a form, I will circulate a form, and that form you can fill. Okay, so that way we will get to know the groups.
Okay.
Okay, so yeah. Okay. Okay, so now, so today, last couple of classes, we are staring at the code, and we are staring at the code and trying to understand what it is doing. Today we will, in last class also we looked at little bit of analysis based on using Amdahl's law. And yeah, so today we study a very, very important idea, a very cool analysis technique called as roofline analysis. So we will first look at try to study roofline analysis from using CPU as an example. And then later we will can see how that those techniques can be applied uh, to FPGAs. Okay. Let me share. So there is, I will post this paper. This is very extremely very cool paper. You should all read this paper. Uh, so when we are trying to optimize uh, a program, that is, we are trying to improve the performance of a program, we need to know we need to, so we keep on trying to do something. We change this and see what is happening, we change that what is happening, like you do loop unrolling, and then maybe you do tiling, you keep on, based on some intuition and experience, we try to do a bunch of things uh, to see that to improve the application performance gains. Uh, so when during that process, couple of things, if we have some clarity on what we are trying to accomplish, like for example, what is the possible peak performance improvement that we can make? Like for Amdahl's law, what we studied in the last class is just one tool, very minor tool, which tells us, like in what is the best case speedup that you can get. So that is one example. But we need to get a more detail. We can do a more detailed analysis. Okay, so what is the peak performance that is possible? And that's number one. Number two, what is it that is preventing me or preventing the program from achieving that peak performance? Two important questions. What is the peak performance gains that are possible? And the second question is what is it that is preventing me from achieving that application performance gains? And how can we overcome these obstacles to move towards the possible peak performance that we can achieve using the underlying system? So here, just 1 minute. So we will use these pictures and try to understand what is happening. So one important thing that one important term that we need to understand is what is called as an operational intensity. The operational intensity we already defined, like the number of computations So right now we are all talking with respect to regular processors, multi-core processors. We will, once we get a good understanding here, we will switch gears and see how these ideas can be carried forward and applied to the context of FPGAs. So the first idea is what is the, so if you take any compute system, any processor, there is a peak floating point performance that is possible. Usually people try to compare, check the performance of a processor by looking at how many floating point operations per second that processor can, that particular processor can perform. Okay, so how many floating point operations per second? Okay, so here let me use whiteboard for a moment and then. So first important is we are talking about CPUs, and so we want to, this is flops, floating point operations per second. So usually, when we think of flops, we use gigaflops, giga floating point operations per second. So giga means, here this is, it's not 2 power 30, it is 10 power 9. So let's say if a particular processor, if it is able to achieve 2 gigaflops computation power, then that means it can do 2 times 10 power 9 floating point operations. They can be addition, multiplication, whatever they are. Okay, 2 gigaflops means this many 2 gigaflops. 2 into 10 power 9 additions, FADs, floating point additions, add, mults, etc. Okay, and so teraflops means 1000 gigaflops is 1 teraflop. 1 T flop, 1 teraflop is 1000 gigaflops. So if you take a processor has some raw compute power that is possible. Okay, depending upon how the arithmetic and logic unit is designed, and different parameters. Every processor, it has some peak floating point performance that is possible. Okay. And so we would like to, that is a raw compute power. So if you look at no, so we kind of get what is called as a raw compute power. And even this raw compute power is kind of obtained by using some benchmarks which are kind of very compute intensive. So there's every processor will have some kind of raw compute power. So if you go look at any Intel processor, that particular data sheet may say the peak floating point performance that they are able to see is in between the range of 600 gigaflops to, they may give some range like this. This is the range of computations they are able to see or something like that. So if you go look at the data sheet of a processor, you may see something like this. Okay. So, and then the next idea which we have seen, which this definition we have already defined, is operating intensity or compute intensity. It is operations per second, ops per second. Floating point, ops per byte of data that is fetched. Ops per byte of data. Like for example, in the VAD example, vector add, we bring 2 array elements, 8 bytes, and we do 1 addition. So we said the compute intensity or the operating intensity is 1/8 in the case of VAD. Okay, so this is the example that we have been working with. And then the next idea is the idea of memory bandwidth. So right now, we'll come to FPGAs later. So let's say even between a CPU and memory, and we know, like we have the CPU does the computations, and then the instructions and the data to the CPU are fed by this RAM. And no, so depending upon the memory, like whether it is DDR4 or DDR5, and the frequency at which no, this memory controller, this system operates, the memory bandwidth may range from 16 Gbps to 64 Gbps. I would like you to check all these numbers by yourselves also. Okay. So this is the memory bandwidth. This is the memory bandwidth. Okay. So we have three things I would like you to remember. So this is the memory bandwidth. Let's call it as a third thing. And the second entity is the operating intensity or compute intensity. And the first thing is the raw compute power. Maybe, yeah. So the raw compute power of the processor. So these are the three things we need to keep in mind. So with these things in mind, so let's try to understand uh, how we can understand, given an application, how we can analyze the performance potential of the application and the performance bottlenecks of the application. Okay, so here, if you see this picture, I should have just focus on what I point, So I know this is not the right way to do, just showing it right away from the paper, but still. So here, if you see the graph, if you look at the graph 1A, this graph corresponds to an AMD processor, Opteron X2. It has two cores in it. So if you take an application, and if you look at this particular processor, the peak floating point performance that is possible for this processor, if you see this, it is 16 gigaflops per second. In Opteron X2, the peak attainable gigaflops per second is 16 gigaflops per second. Okay, this is what you are seeing. Great. And it so turns out the memory bandwidth here, as per the benchmark, they did the benchmarking using some application. The memory bandwidth also is something like 16 gigabytes per second. This is the memory bandwidth. I'm using MB for short. So memory bandwidth is 16 gigabytes per second. So if you have an application with whose operational intensity is half, okay, that is, it is like if the operations per byte is half, that is low operational intensity. Then if you can see the peak, the floating point performance that you can get for that particular application, that is the number of gigaflops per second, which that particular application can obtain, is half into the rate at which you can stream the memory, and it is 8. Okay, you will see somewhere here. Okay, so the operational intensity, that is, you are hitting that means it's very important that you are not able to realize the peak performance which that processor can give, because the operational intensity is low, and you are able to, the rate at which the data is being streamed, it is 16 GB per second, you are only able to get 8 gigaflops per second. Okay, so then in this case, we say that the application is a memory bound. We say that the application is memory bound. And then there is another application whose operational intensity is 2. Uh, so since its operational intensity is 2, and it can with 16 GB per second bandwidth, uh, so it can it can perform 32 gigaflops per second operation, but unfortunately the CPU is not able to do that many gigaflops per second, so it hits the roof here. This is why it's called as roofline analysis. So here it's a compute bound application, and we will not be able to improve the performance of this application no matter what, because the peak floating point performance for that particular processor is 16 gigaflops per second. Okay, so there is no point in, when you are here, there is no point in spending your energy in trying to optimize this program further. That's it. Okay, you hit the roof, you hit the ceiling, you cannot improve the performance. And if you can somehow, if there is an application which is memory bound, and if we can somehow increase the operational intensity of the application one way or other, let's say from half to 1 at least, then what happens is then we will hit this what is called as a ridge point. This ridge point, if we can hit this ridge point, then by moving from left to this, then we will be able to, then at this ridge point, memory is no longer the bottleneck, compute becomes the bottleneck, because the processor is not able to do much. So if we can re-architect the application somehow, and be able to increase the operational intensity from half to 1, then we are good. Okay, then we are able to use the processor to the best of its abilities. Okay. So here Prithvi has a question. The time taken here is the total system latency. Yeah, that's true. Yeah. So here we are not even measuring the latency here. No, we are just trying to see what is the peak floating point performance of the application. That's what we are trying to analyze. So this also helps the processor designers also in a way, because if you just keep the memory bandwidth and if you just pump up the power of your arithmetic and logic unit, then the application developer has to really struggle. He may not even be able to use uh, all the gigaflops you are providing, because he is seriously constrained by the memory bandwidth. Like for example, you are designing a processor and you say my processor can perform 1 teraflops per second. So in order for you, and right now the operational intensity of your program is half, in order for you to hit that 1 teraflops roof, 1 teraflops means 1000 gigaflops, your operational intensity of the program has to go from half to maybe 100 or 1000 something like that. So, when processor manufacturers also, they should not blindly just jack up the hardware resources for computations, because the bottleneck, because of other bottlenecks, you will never be able to use all the compute power which you are providing to the programmer. Great. So now let's move to any questions here. We can. These ideas are very important and very cool. No, once you get a hang of this, then when you're trying to accelerate applications, be it FPGAs or GPUs or CPUs, these things will really come in handy and drive you in the right direction. Any questions? Okay, so quick question. Let's see. Let's see how you are doing. Let's say there is a program whose operational intensity is 4. Okay, so there is one particular program. So its operation, it is sitting here. And if the its operational intensity is here. If we kind of if the peak floating point performance is 1 teraflops, then in order to hit that roof of 1 teraflops, how much the operational intensity should increase? You understood the question? So right now, in this case, the roof is 16 gigaflops. I'm saying the roof is not 16 gigaflops. The roof is the compute roof. The compute roof is 1 teraflop T-flops per second. Okay, and the application's operational intensity is 4. Okay, if the application's operational intensity is 4 and the memory bandwidth also remains the same. Let's say the memory bandwidth increased from memory bandwidth increased from 16 GB per second to 32 GB per second. I'm just changing the number so that you'll think, okay, GB per second. So how much should the operational intensity, how much that the program should move to the right so that it will hit the compute roof? Quiz. No answers? You're all sleeping or? It already is at compute roof, huh? How is it? 32 GB per second, and it already hits the new compute roof I am saying is 1 teraflops. There is a new processor that is out there. There's a new processor that is there which can perform 1 teraflops.
Sir, if we increase it to like 10, then it will go to 1280.
Sir, how do we compute this, the slope of this uh, peak memory bandwidth stream? So based on that, it would be depending where it would intersect with that horizontal line of the peak, right?
Yeah, so let's see. Let's try to work this number. You should help me. I just cooked up the whole thing. So the first thing that we have is peak. We talked about these things, right? Number one, peak compute that is possible is 1 teraflop per second. Okay, this is the first thing that is. And then memory bandwidth is from 32 GB, from 16 GB, I increased the memory bandwidth to 32 GB per second. Okay. So, and then what is the third thing? The current operational intensity, OI, just use it, is 4. That is 4 operations per byte or per unit of data. Then if you see, then if you see max flops achievable at current max flops, maximum flops achievable at an operational intensity of 4 with memory bandwidth 32 GB per second is 32 into 4, which is 128 gigaflops. Are you all with me here? Does it make sense? This is what we can do. Given the memory bandwidth, given the current operational intensity, we are able to go to we are able to get only 128 gigaflops. Yes or no?
Yes, sir.
Okay, so this is now, is this a memory bound or compute bound? This is memory bound, right? Because the roof is the peak, because of the memory bandwidth. If you increase the memory bandwidth from 32 to 64, then the flops will also increase. So that's an indication that memory is the bottleneck here. So right now, this is memory is a bottleneck. This application is memory bound. By increasing the bandwidth, we will be able to go from 32 to 64. We are increasing the roof height, and we will be able to get 256 gigaflops just by increasing the memory bandwidth. We don't do anything about the kernel. But somehow if we can increase in order to, so what we would like to do is the memory bandwidth remains the same. So 32 into the memory bandwidth remains the same. And we would like to know what is the operational intensity that should be there, so that we get 1 teraflop. 1 teraflop is, so let's say 1000 gigaflops. I'll write it as 1000 since let's working in gigaflops. So this is what we have. So the operational intensity, or maybe in order to kind of make it slightly simpler for us, let's say we use 1024 as an approximation. So the operational intensity, if it should be 1024 divided by 32, this is 2 power 10, this is 2 power 5, this is 32. So the operational intensity, if it goes from 4 to 32, then we will hit the compute roof. Are you all with me here? Does it make sense?
Yes, sir.
Okay, so this is, please understand this. This is a very basic example. If you understand this, then it helps you in many places. Okay. And yeah, so now let's look at the Opteron X2, X4 is a 4-core processor, and possibly it may have some SIMD lanes in it, that is vector lanes in it. And because of that, the available gigaflops in Opteron X4, it is somewhere around 64 gigaflops per second. And for X2, it is this. So now if you take an application with with the operational intensity, whose operational intensity is 2, if you take an application whose operational intensity, if you have questions, you can unmute and also ask, because I'm not able to see chat all.
Sir, is the graph always linear, sir, in this?
Graph linear,
I mean, you're
who is
just talking
asking this
about.
question?
I'm 50%, sorry.
Graph linear, Well, at least in the simplified, uh, yeah, usually in the simplistic, we are doing some kind of rough cut analysis. In these cases, the graph may look linear. Yeah,
Yes.
yeah,
Okay. Just ask me something. Okay.
yeah, yeah.
Thank you.
So now if you take the same application whose operational intensity is uh, 2 and go here. So now here what happens is the operational, so the you will be hitting suddenly it becomes a memory bound thing. Okay, it becomes a memory bound. And that's what we tried to do. No? Earlier, what happened? We increased the ceiling from 16 GB to ridiculously high 16 gigaflops per second to 1 teraflop per second. And in order for it to be compute bound, the operational intensity has to be extremely high. But in any case, if you see this application, the same application on Opteron X4 with 4 cores, it is a memory bound application. So that is the reason when we have an application and when we try to the same program, you can just compile the same program and run on an X4, or even you may not even compile it, even the binary compatibility might still be there. But while the program is portable, it's not performance portable because you have to re-optimize your kernel, your whatever the application, so that it uses the new system to the best possibility. Okay, so because of these things, there are what are called as auto-tuning libraries. That is, you write a library. Libraries are usually portable. They are written in a way so that they are portable across platforms. But in order to make them performance portable, so they'll be written in some kind of uh, parametric form. And when we install the library on your machine, you just install all the dependencies and everything goes like that, right? But these auto tuning libraries, like for example, there is something called as an Atlas. This is Atlas does, if I'm right, basic linear algebra operations. So BLAS. BLAS stands for basic linear algebra system. So this Atlas library, when you try to install on your machine, it tries to kind of reorganize or try to find the optimal parameters so that it moves towards the compute bound side. Okay, so these things happen. Okay, the key thing I want you to remember is performance portability. So when you are working with FPGAs also, like in the FPGAs, there's a whole spectrum of FPGAs, embedded systems to data center FPGAs. So while the same OpenCL code that you have written, the hardware design that you have given, while it may be good for an embedded system, it may not be good for a server class FPGA. Okay, so you have to retarget. The code might be the same, but instead of having one compute unit, you may want to have 4 compute units or do some other things so that you can port your hardware accelerator uh, so that you can use the underlying system's capability to the best possible extent. Okay. So now let's get going, and I'll clear my screen. How many of you are feeling good or thinking this is fun? I felt really good when I looked at this picture for the first time. Such a clear, simple analysis of where we are heading, what are the issues. No, I felt really good. Okay. So now we look at couple of one more example from this from the CPU space itself, and see how how things could work for you. Okay. So now we are still working now. Right now, if you see the leftmost figure, we are still looking at Opteron X2 processor. And in the Opteron X2 processor, so if you just use, right now, so far we are just talking about memory is the bottleneck and blah, all that, right? So, but then, so Opteron's peak floating point performance is 16 gigaflops per second, and it has 2 cores in it. So if you see the line, this particular line, TLP only, I think it stands for thread level parallelism only. So if you have an application where you are using only thread level parallelism, okay, you are just using the 2 cores, then the peak achievable compute performance is 2 gigaflops per second. You hit the roof. No matter what you do, then you are not actually hitting uh, the memory bandwidth. Okay, you are not hitting the memory bottleneck because you are having 2 threads and you can do 2 gigaflops per second. So there is no issue. So the memory bandwidth still is 16 GB gigabytes per second. Just keep that in mind. And now, so if you go beyond thread level parallelism and try to use the SIMD lanes in each of the cores, that is the vector instructions, vector units, vector processing units in each of the 2 cores, and also exploit instruction level parallelism. You don't need to do it by yourselves, but the compiler will try to do it for you, at least the ILP part. Then what happens is the achievable gigaflops goes to 8 gigaflops. So once so you have initially you started let's say initially you started somewhere here, your operational intensity, you have a kernel. This is a version K1 of the kernel. In the version K1 of the kernel, it is only using thread level parallelism. It is able to get 2 gigaflops, and no, memory is not the bottleneck. So yeah, you felt good. You're all great. And then so some others, and then you realize, hey, why don't I use SIMD units? And once you use the SIMD units, then you can actually perform the achievable gigaflops becomes this, the achievable. But then, so while you are trying to go hit this peak, what happens is, the SIMD unit wants lots of data to process, but your memory is not able to give the data at that speed. So memory becomes the bottleneck. So memory becomes the bottleneck. Once you modify the kernel you to use the available SIMD units, then your processor becomes more data hungry and your memory is not able to provide data at that same speed. So now what you have to do is, so that is version K2 of the kernel. So original version is K1. Okay, so this is TLP only. The second version K2 is, this is TLP is compute bound. And as version K2, it uses, TLP plus, plus SIMD. And then it becomes memory bound because you are processing, data at a very high speed, but memory is not able to support it. So now what you have to do is, you try to increase the operational. So now the version K3 of the program, you try to do some optimizations so that your compute intensity, the operational intensity increases from 1/4 to half. So once your operational intensity increases from 1/4 to half, you are at this ridge point. So you are good. So this is, so you did some memory optimizations. Okay. Some memory optimizations you are doing so that again it becomes compute bound. And then what happens is in your application, usually what happens is, so if you have a good mix of addition and multiplication operations, then it becomes easy for the ALU to give better performance than all multiplications. So maybe you can do some program changes so that you will get a good floating point balance, floating point operations balance, and which again increases the attainable gigaflops to 16 Gbps. So once the attainable, and then K4, you do some, FP balancing, floating point operation balancing you try to do. I hope you are able to follow my line of thinking here. FP balance. So when you do some FP balancing, then again, so what happens is you can, again, your processor is able to do a lot more computations, and again, you suddenly know your operational intensity is not sufficient enough to, because memory bandwidth is going to remain the same. This half is not sufficient to satisfy the hunger of the CPU. So you have to work for a new version of the kernel K5 so that you move from increase operational intensity from half to 1, and then so that you get the peak floating point performance. So this is the story. So you can see by using this roofline analysis, you can develop a series of kernels, identify the bottlenecks, okay, in your system, in your program, and then keep developing increasingly more better performing kernels. I would like to take a pause here and want to check how many of you are with me so far on this example. Can I see a raise of hands to see how I'm doing, how we are all doing together? So I hope you are happy and excited about this discussion. Okay, good. Nice.
Hello, sir.
Yeah.
Sir, here FP balance means what?
FP balance is, I am trying to understand. So if the floating point operations are all multiplication, then the multiplier units in the ALU will be more loaded and the adder units could be idling. So, but if you have, let's say, 50% multiplication, 50% addition, I'm just picking some random numbers, then what happens is you can keep both multipliers and adders busy. So thereby, that you can achieve more gigaflops.
Okay.
Great. So now we talked about optimizations associated with to lift the compute roof up. Okay, to lift the compute roof up. And with memory also, we have these things. Like, for example, when we say the peak memory bandwidth is 16 GB per second, what happens is it is just, you may just read a 16 GB sequence of bytes from the memory and loop through the CPU, and through that you will get that 16 GB bandwidth. But then, if your program has, if you are accessing, if you are, let me write a small code here. If I have something like, if I have a code something like for I is equal to 0, I less than or let's say put it in a different way. Yeah, let me give two examples here. I less than some n, I is equal to I plus s, and you do some computation here, and here you are accessing let's say array elements a of I, b of I, c of I, for example. So the S you're accessing, you're not accessing consecutive elements of the arrays A, B, and C. You are accessing every S. Let's say if S is equal to 4, you are accessing the every fourth element of the arrays A, B, and C. So this is what is called as a strided access. The stride is 4. So when the stride is 4, the spatial locality of the program will be bad. And because of that, the net bandwidth that you experience will be way less than the peak memory bandwidth that is achievable with respect to your program. Because you get data and then you discard it. You get data and discard it. Because, you may have, in the last class, Prithvi is mentioning that even if he accesses, let's say, a particular word in the memory, the surrounding 512 bit, the surrounding 16 bytes are automatically fetched by the DDR controller. Well, it depends on the DDR controller, but many DDR controllers, they may kind of want to do it, so they do it. But then if the stride is big, then you fetch the data and you discard all the surrounding data because it's not useful for you. So big strides are bad for you. The net memory bandwidth you can utilize is less. If you are not happy, this is all right because the stride is uniform stride. That is, your all the time the stride is 4 or 6. But let's say you are trying to do a tree traversal. You start with the root node, you go to the left child or right child based on some comparison. Then there is no stride. You are all over the heap memory, and the memory bandwidth just falls apart. So those are called as irregular memory accesses. So regular memory accesses versus irregular memory accesses, and uniform stride, unit stride versus stride which is greater than 1. So these two things I would like you to remember. So let me write down here: regular versus irregular. Number 2 is unit stride. Unit stride is good. The spatial locality is very good versus greater than 1 stride, large stride. Okay. So stride increases, locality decreases. So this is, so both these things, they relate to the spatial locality of the program. When you're studying CSO, no, you study temporal locality and spatial locality. Yeah, it's a very important thing. The way we are going to increase this operational intensity. So when we are working in this space, the way, if you want to go from here to here, somehow we have to exploit temporal locality. That is, a data item that is used now, it will be used in the near future. In order to increase the operational intensity of a program, we rely on the temporal locality. And in order to kind of increase or utilize the maximum available memory bandwidth, we try to go from irregular memory accesses to regular memory accesses, and from strides which are greater than 1 to try to move towards unit strides. So now if you see, you can see here, there is, while the peak memory bandwidth line is here, with, let's say this is 16 GB per second thing. And for a variety of reasons, you don't get that full 16 GB per second, but by kind of working with your program, you can get that 16 GB. We can, let's say, get maybe this is 4 Gbps per second line. Let's say this is 4 Gbps per second. Okay, so by The original program, it's all the memory access patterns are not good. You worked out, you rehashed your code, and then so now it has a unit stride. Because of that, you are able to get 4 GB PS per second. Okay, so when you have such low, when you have such a low um, uh, memory bandwidth, the roof line you will be hitting here. Let's say you have a kernel with operational intensity half, then no, you will hit the roof line very close. Okay, so here you are. So now what you can do is you can kind of do some more memory optimizations, so that like if you have a, let's say if you are working on a uh, let's say you have an application, so let's say you have a hardware architecture. So this is one processor, this is another processor, both the processors are sitting on the same motherboard, and there is a memory, your memory is a distributed memory, and so the M1 is local for processor P1 and M2 is non-local. Similarly for P2, M2 is local for P2 and M1 is non-local for P2. If you kind of allocate your data in such a way so that the threads that are running on P1, their required data is on M1, and the threads that are running on P2, their required data is on M2, then the effective bandwidth you might be able to increase from 4 Gbps to maybe, let's say, some 8 Gbps or something like that. Okay, 8 or 12 Gbps maybe. So when we increase the memory bandwidth from 4 Gbps to 12 Gbps by reworking your code so that the memory is appropriately allocated, then what happens? Then your effective this goes up. Okay, so the roof, so the achievable gigaflops, it will be this. It will be this. Okay. And then after that, you can do more optimizations like software prefetching, using which if you prefetch the data before you access it. It's not quite easy to do it in all the cases, but let's say if it is possible for the particular application. So using that, if you are able to get the max 16 Gbps per second bandwidth, then for the same operational intensity, you get the best possible gigaflops achievable. And once you hit the roof and no, it's no longer possible for you to do any more memory optimizations, then you have to switch try to see, but you still see that the processor has the potential to do more computations, then you try to move in this direction. Okay, they try to increase the operational intensity from half to 1 or 2 or something like that, so that you can get the best performance that is possible from your system. Okay, so through memory, so what we are doing is through memory optimizations, we are moving this this thing in this way, and through compute optimizations, we are moving the compute roof up. So as we keep moving this up here and moving this up here, then what happens is they intersect higher up, and that you are just lifting up the whole roof, and through that you are you are able to get the best performance for your application. Okay, and in the vector add example, so we did many of these things actually. Like for example, in order to so can you tell me what we did in the vector add example? To what did we do anything in order to improve this roof, lift up the roof?
Loop unrolling.
Loop unrolling. Okay, loop unrolling. That's true. Good. Loop unrolling is yeah. So you're kind of doing multiple operations per through loop unrolling. Excellent. So through loop unrolling, we are we are trying to move this this line up. We are able to do. Earlier, we are able to do some number of computations, but through loop unrolling and having that, having multiple add operations, now we are able to, that is equivalent to loop unrolling is equivalent to SIMD-ifying the thing or increasing the SIMD length. So this is one super interesting thing now. In a processor, the SIMD length is all the time fixed, six multiplications in parallel or 8 multiplications in parallel or something like that. The SIMD, since it's an ASIC, the SIMD length is fixed. But in an FPGA, you can unroll it and you can create new, configure new things on the fly. On the fly means at the design time. Because of that, it's what you can achieve. It is substantial. Okay, so through loop unrolling, we are able to increase the operations per cycle. Okay, so what happens is you keep on unrolling. At some point, what happens? So at some point, so let's say here, let's say initially the peak memory, your compute is something here, and you keep on unrolling. And as you keep on unrolling, at some point, what happens is this line will hit here, and the memory becomes a bottleneck, and rather than the hardware, rather than the FPGA logic that is present. Okay. Anyway, so this is loop unrolling. So what is the, let's say this is a problem. You keep on unrolling. At some point you figured out, compute is no longer the problem, but memory is the problem. And what do?
We did like we did increase the channels, no?
Yeah, awesome. So I'm very happy now. So number one, we kept on increasing. We of course um, we just did an unroll by constant factor. But that's an interesting question. Like, okay, so you keep unrolling, and at some point, what happens is memory becomes the bottleneck. At that point, instead of focusing on this, you try to focus on the memory. And there, what did we do? We increased the bandwidth, the bus width to 32 bits to 512 bits.
512 AP underscore N.
Yeah, that's true. 512 bits. And not only that, we used 3 DDR memory banks. Okay. So that is how we kind of worked on the memory. And then maybe after having the memory, increasing the memory, there are 2 possibilities. Now it may give us more scope for increasing, more unrolling could be possible, or maybe no, we already did a lot of unrolling. In spite of that, and in spite of having got everything that is possible from the memory, no, we are that's the best we could do. Then at which point you may even consider decreasing the loop unroll factor and thereby save the resources on your FPGA. Are you with me on this line of thinking? So just focus on 2 things and how things played out for us in this simple example. Loop unrolling, through loop unrolling, we are increasing the SIMD lane length, and we are able to do more computations per second on the FPGA. But for, let's say if you have a SIMD of 1,000 additions per second you can do, but the memory is not able to supply 1,000 elements per second, then what's the point of using that many resources on the FPGA? Let's say the max you could do is 600 additions per second, in which case you can reduce the loop unroll factor to 600, and so that way we kind of hit the ridge point. Okay. Are you all doing good? So one more check. Happy? Good.
Sir?
Yeah.
Yeah, can you please explain the memory affinity, how we increase that memory band?
Memory affinity in this particular case, in the case of CPUs with with a one processor with 4 cores, this memory affinity is not quite clear to me, Kalesha. So, but if it is so if you look at memory, there are two kinds of uh, systems. Let me use a white stop share. So this memory affinity, let's look at the simple case. Usually in our system, what we have is, we have the CPU and maybe it's a logical picture. I'm not sure. I might be missing something. This is your RAM. In this particular case, I am not exactly sure about memory affinity unless this RAM itself is divided into multiple banks and some kind of low level things you can do. Maybe Lavanya or Padmini can shed light here. But the other case I know for sure, if you have if you have a distributed, in many server class machines, on the same motherboard, you will have 2 processors or 4 processors, let's say P1, P2, and then you can have distributed memory. Your RAM is distributed. And there is some kind of interconnect connecting these processors to this RAM. So this is RAM 1. So let's call it as, instead of RAM 1, let's use it as M1. This is M1, M2. So as I said, no, the M1 is local for processor P1 and M2 is non-local. So the threads that are running on P1, if the associated data, if you can pin them in memory M1, then the local access time is less than the non-local access time, because when you are trying to access a non-local memory module, you have to go through some kind of interconnect or some kind of logic will be there. So there will be some contention, etc. But local you can access fast. So if you can do some kind of optimization where T1 accesses this chunk of data and this chunk of data, T1 runs on P1 and associated chunk of data is mapped to M1, then that is your binding it. So there you can get in more bandwidth because you don't go through the interconnect network to reach out to data. Okay. But if it is, and in the case of FPGAs, yeah, in the case of FPGAs also, do you remember, no, we were talking about SLR regions, SLR0, SLR1, SLR2, and so a logic that is present in SLR0, and then, yeah, this is an approximate picture. So this is SLR0, SLR1, and SLR2. And for every SLR, there is some kind of, the memory is local, I think. I'm just giving a rough picture. I might be wrong here, but we have to double check. But in the discussion in the class and in the manual that we read also, if a logic that is present in SLR0, it tries to access this memory bank, and between these, whenever there is a signal or some kind of propagation needs to happen across these SLRs, there will be some routing happens. Because of that, there will be delays. Okay, so all these things, if you kind of avoid these things, then effective bandwidth that is achievable goes up. Okay, does it make sense or?
Yes, sir.
So Lavanya, Padmini, you want to add something here or?
Yeah, I could add. Go ahead, Lavanya.
Nothing. I just wanted to say that the previous diagram which Suresh drew, right? That is what I also wanted to add with the distributed memory. Yeah, this one. And basically, the interconnect, you'll have these MISI kind of protocols where it's mutual, exclusive, shared, and so on. And hence, if it is logged to M1, like he said, it will be faster. But instead of this being the final memory, in the cache hierarchy itself, you will have an L2 shared cache, which is kind of distributed amongst all the cores. So the latency dependencies will matter on whether the L2 cache is exclusive to core 1 or it's shared between core 1 and core 2, and how you're pinning the regions in the L2 cache accordingly. Because you'll not have a lot of what do you call it, data thrashing or cache thrashing, where core 2 is replacing a particular cache row, and then core 1 is again accessing that, and it's a miss and so on and so forth. Yeah. I don't know if I'm clear or any doubts or questions.
Yeah, I think understood, Lauren. At least I got it. Yeah.
I spoke too fast. I think I should be a bit slower.
I think if they don't know that that Missy.
I think Mayank and Adarsh have raised their hands. So please go ahead. First Adarsh and then after that Mayank.
Yeah. Sure.
Oh, they have lowered their hands. Adarsh,
That was in response to a previous question.
Yes, that was a previous slide.
Oh, okay. So any other questions? I don't see anybody else raising hands. Sorry, Padmini, you wanted to say something, I think.
And the next one, in addition to SLRs, the other way you can think about optimizing throughput is also through, how you design the usage of memory inside the FPGA dies themselves. So if you remember, there we have distributed RAM, block RAM, and ultra RAM.
Yes.
And exactly how you map, how you fetch the data that you need, and how you architect the memory inside the FPGA also will make a difference to the speed of computation.
Yes. Very nice. Actually, that is the next thing that I wanted to discuss. Yeah. So, but I'm thinking maybe I will pause here and I will let them think about these ideas. And in the next class, what we will do is we will see how we can apply these ideas to the FPGAs. Okay. And how we can drive the design. Important thing, so I'll just give one quick example, and then we will continue this discussion in the next class. So yeah, so here, so let's say in the last we were looking at VAD operation, right? Vector add is kernel is what we were looking at in the last couple of classes. But let's say you are working on a what do I say? Yeah, fingerprint detection system. Okay, you are working on a fingerprint detection system. So this is our Aadhaar card. No? So this is Aadhaar. So what happens is in our database, so the fingerprints associated with all the citizens of India. So what will be there, and so usually, so I'm giving an approximate picture. I'm not sure if it is accurate, but let's say we feed this fingerprint to some kind of CNN. And it generates a feature vector representation of the fingerprint. It's a vector, feature vector. So every fingerprint is represented in the database as a vector. And the dimensions of this vector could be, let's say, 256 dimensional vector. Every element could be a floating point element in this vector. Okay. So that is how, let's say, our fingerprints are represented in the system. And now, given a new, and then there could be million or billion fingerprints in the database. So given a new fingerprint, so the question is a new finger. So we want to query, like for example, when you go and want to register, you, let's say, land or something like that, you give your fingerprints and it tries to match whether it matches what they have in the database. So let's say, so new fingerprint, so there is a new fingerprint query, query that comes up. So the query is also a vector. So you take your fingerprint and again, we compute a CNN, we pass that fingerprint through a CNN and you get a query. And what we do is, let's say in the database, we have all these fingerprints F1 to Fn, where everything is a vector. I'm using, let's use, and then you have a query. So let me, where do I get my writing pad? Okay, I'm not able to erase it. So you have the query queue, and what we want to do is we want to, in order to check whether this query Q bar is nearer to which of these n fingerprints in the database, you compute the dot product. You try to do cosine similarity. You compute, Q bar dot Fi bar for all I running from 1 to n, and you try to take the one which is close to 1. When the two vectors are in the same direction, so their dot product angle between them is equal to 0, and their dot product will be approaching 1. If they are diagonal to each other, the angle between them is 90, and when you take the dot product, it becomes equal to 0. So we have the cosine similarity measure. So if you try to do this using an FPGA, then what happens is, if you think of the operational intensity, in order to compute, so when you are trying to do this dot product, so what happens, it is something like, let's go to the next slide. So we have something like for I is equal to 0, I less than 256 plus I, A is equal to A plus Q of I times maybe F of I. Okay. And there could be outer loop, and then instead of having F of I, you may have F could be double indexed, but for the time being, if you just leave it aside. So if you see the operational intensity is, so what the heck, so I will use outer loop also. This outer loop is to iterate over all the elements in the database. Let's say there are this many elements in the database, plus J, you'll have this, and then instead of, you'll have, I'm not able to find the eraser, so that's why I'm overwriting. Apologies. This is Q of I into F of Ji. So this is F of J, F of I. So if you see the actual computation that is happening here, there is one multiplication and one addition. This is what is called as a multiply and accumulate, MAC. So there is one multiply and one addition happening, that is two operations for 8 bytes of data. That is Q of I, if you think as 4 bytes, and F of Ji is 4 bytes, then there are 8 bytes. So the operational intensity is 2 by 8, which is 1/4. Okay. So this is pretty bad. No, this is pretty bad. So we would be almost all the FPGA compute resources they could be idling. We would seriously be bottlenecked on the by memory. This is a seriously memory bound program. But what we can do is, no, instead of usually when we do these queries, the query, it's not like you are the only person who is querying that thing. There are multiple centers which are sending these queries to the database. And if we can batch these queries, okay, so if we batch the queries, okay, then what happens is, let's say the size of the batch is capital Q, then as you stream in these the fingerprint database into the memory, and we are trying to do, we do queue parallel things, computes. So because of that, what happens now is the operational intensity of this batched program, it becomes q by 4. Earlier it is 1 over 4, now it is q over 4, q times 1 over 4, because we are batching q queries per second. Uh, so, uh, so now we can keep on increasing queues to get a very good operational intensity, so that we can get the peak bandwidth. But then just by increasing queue, it's not sufficient, because the queries that we have batched, and these batched queries, they will be stored in the VRAM of the memory. Okay, you don't want to stream these queues again and again. It beats the purpose. So you have all these, you take a batch of queries and you store it in the VRAM of the FPGA, and then you stream in the rest of the fingerprint database, and you try to get the closest match. So through batching, we can improve the compute intensity, but it doesn't come out just like that, because when you have queue things that are there, you have to organize or store these queue queries in your VRAM in such a way so that the VRAM bandwidth wouldn't become a bottleneck. So each query, like for example, if you want to do queue parallel operations, you should be able to do queue reads. So then that means, let's say if Q is equal to 1024, is it possible to do 1024 parallel reads in your FPGA? So how do we organize stuff, no? The data that we present on the FPGA, so that that wouldn't become the bottleneck, okay? So when we study, when we in the next class, when we look at this thing a bit more closely, so we will also see that once we kind of overcome certain memory bandwidth issues, we have to be clever within the FPGA also to see that no, the way we store the structures, the data within the FPGA, they don't, they give us, they provide maximum on-chip bandwidth for us. So with this, I will revisit this example and try to, and we look at this more carefully in the next class, okay? Yeah, go ahead.
Can you go to the previous figure? So here you said that operational intensity is 2 by 8, right? So it's like one multiplication, one addition. So there are two operations, but
yeah,
it's that is not on the same bytes, right? So it is different. So why the byte means 8 bits? So what is you are keeping there in the denominator? Is that correct?
8
Can you
is, I'm thinking Q and F. 4 bytes for Q, and you can think A is there on the in a register.
Okay.
Okay, so however you perform computations inside, so you are performing two operations per 8 bytes of data that you have fetched from the memory.
Yeah, assuming Q and F are 4 byte
Yeah,
unsigned integers.
yeah. And if you think that Q is just staying in a register array in the FPGA, then this becomes 2 by 4 or something like that. You just bring, you just stream f of ji, in which case the operational intensity becomes 2 by 4, 1 by 2.
Okay.
Okay.
Sir, why 2 by 4, sir?
If you assume Q is present in some register array, because you get the query and you store it in some register array inside the FPGA, you only stream this. So the initial cost of just bringing Q is negligible, so we can just keep that aside.
Yeah, but here 2 is representing the multiplication and addition.
Addition, but 4 is for if you are not getting q, no, every time, then the only data that you're getting is f of ji, which is a 4 bytes length.
Okay.
That's way. Okay, so I think we should stop now. I would like you to think about today's lecture carefully. Watch the video if it or I will post the paper also. Please read the paper and come prepared to the next class. We will try to apply these principles to the context of FPGAs and see how we can use these principles to drive the design ideas there. Okay. That's all for today. It's a Saturday afternoon, 1:30. Everyone will be hungry. Yeah, so sorry.
Just one last thing. Can you post the office hours when you will be available for any questions?
Okay, I will do it. Yeah.
Okay.
I'm delaying everything, so I will do it. Yeah, sure.